Hello everyone, welcome to the course of Gate Crash course offered by Geeks for Geeks. My name is Puneet Kansal and I'm mentor at Geeks for Geeks. Hello everyone, welcome to the course of Gate Crash. So in this session, we will discuss about one of the most important topic in DSA, that is sorting and searching. People like to ask the questions from interview. In interview, they like to ask the question from sorting and searching very much. And in this session, I will try to connect this session not only from gate purpose but from your DSA preparation or point of view also. Okay. So you will what will the benefit? Let me tell you first. What will be the benefit after attending this session is uh, we will cover the most important questions asked related to sorting and searching in interviews, and we will cover the most important top concepts related to that. How these what are the different sorting algorithms are there, and how they work actually, and what can be the most important questions generated from them. Okay, so we will cover all of these things from sorting and searching from both these areas. Our more focus will remain on sorting because this topic is little lengthy also and important also. Okay, so let me before starting this topic actually, uh, you people can write in the chat box. Okay, you can confirm me if I'm properly audible or not. Okay, please write in the chat box if I am properly audible or not. Meanwhile, let me tell the new people here that okay, this session is the part of the Gate Crash course offered by Geeks for Geeks. This Gate Crash course is free of cost. You can find out the detail in the description. Let me give you little brief introduction to Gate Crash course. See, so this Gate Crash course is covering actually 5 most important topics from every subject, from all the subjects which comes in the gate, and this can help you to clear the gate exam if you are not sure that you can clear the gate exam or not. So this Gate Crash course can help you to at least clear the gate exam. And if you are already preparing for the gate exam, then this Gate Crash course can help you to revise the most important topics. Okay, so you can take the benefit in any way. And third benefit which you can take from this type of particular session is that, like, this session is related to DSA, which is actually the most important subject, you can say, for computer engineers or for IT engineers. That is the most important subject. So we are covering one of the most important topic from that most important subject. So even though you are not preparing for the gate, still this session is going to help you in your company preparation. Okay, so hello, hi Digit, hi Gate Aspirant 2023. Okay, so my voice is clear now. I can start this session. So we will cover various sorting techniques in this. We will cover various sorting techniques. We will check out their time complexity actually of these sorting techniques. Then we will see the searching techniques, and we will cover various examples. We will try to understand all the things with various examples actually. Okay, so I will cover all these techniques. Okay, and the main focus will be remain in this session is on the on interview based question. But what can be the question asked in after the gate exam, maybe, or even maybe in 1 marks in gate, they can directly ask these type of questions, which I'm going to cover from various techniques used in the sorting or searching. Okay, okay, so let's start now. Let's see various type of sorting algorithms, sorting techniques. Actually, we can broadly categorize sorting techniques in two categories. So one is, we can say that there are some algorithms, there are some comparison based comparison based sorting algorithms are there, and there are some non comparison based. Okay, that's it. Non comparison based So we categorize these, so all the sorting algorithms in two category. Okay, one is comparison based, another one is non-comparison based. What is the difference between comparison based and non-comparison based? Is comparison based means like if you are, if I'm asking you people, okay, I'm asking to you, out of, I'm giving you two numbers, okay, I'm saying that, okay, I'm giving to you two numbers, one is 10, one is 20, okay, I'm asking you which number is greater, 10 or 20. Then what you will do, you will compare 10 and 20, you will compare 10 and 20 with each other, then you will find out that, okay, 20 is greater than 10. After comparing, you will find out that 20 is greater than 10. Then if you are comparing the numbers, if you are comparing the numbers with each other, to find out that which number is greater, which number is smaller, so that you can sort them. Ultimately, we need to sort them. So if you are comparing the numbers, means you are using comparison based sorting algorithm. Okay, you are using comparison based sorting algorithm. But if you are not comparing the number, if you are not comparing the number without comparison, I give you two numbers, 10 and 20. I say, please don't compare 10 and 20. Can you tell me which number is greater? Then what you will say, sir, are you mad? How you can say, okay, which number is greater without comparison? But we can do that. But we can find out, we can use some other techniques. There are some other techniques through which we, without comparing the numbers with each other, we can sort the elements, we can sort a list of elements. Okay, so those type of algorithms in which we are not comparing the numbers with each other, those algorithms are known as non-comparison based sorting algorithm. Okay, so let's see what are the comparison based sorting algorithm, what are non-comparison based sorting algorithm. So I'm going to make a table here in this board, and that table will cover I will say that 5 to 6 questions which are already have come in the exam. So they may ask 1 mark question easily from the table which I'm going to make here. That will be the complexity table, that I'm going to tell you various type of algorithms and their complexity. So first of all, can you write in the chat box all? Okay, can you write in the chat box name of different algorithm, different sorting algorithm, whatever you know. Keep typing, whatever the whatever sorting algorithms you know, keep typing in the chat box. Okay, everyone just keep typing. Okay, so I'm not laughing after looking at 20. Yes, 20 is greater than 10, no doubt. Okay, so you just keep typing whatever sorting algorithm comes in your mind. Then I will tell you, okay, this sorting algorithm is comparison based and that algorithm is non-comparison based. You already know these things. You already know. Just I'm going to sort these things in your mind. Okay, I'm just going to sort these things. You people already know these things. So quick sort, merge sort, insertion sort, quick sort, these are actually part here, these belongs to this area. So one maybe I can write, okay, like bubble sort, selection sort. So these are comparison based sorting algorithm which are comparing the numbers with each other, then finding out which number is greater, which number is smaller. Okay, insertion sort, and after that, okay, let me write the merge sort, quick sort, heap sort. So these are some popular, I'm talking about popular sorting algorithms. These are some popular comparison based sorting algorithms. These are popular one I'm talking about. There are many other also, like shell sort and all. And in non comparison based, there is actually like counting sort, radix sort, and bucket sort. So these are non-comparison based sorting algorithm. Here we will not compare the numbers with each other, but still we will be able to find out which number is greater, which number is smaller. Okay, so these are comparison based, where we are comparing the numbers with each other, then finding out. Okay, let's now talk about their time complexity in term of, okay, let me categorize them like best case time complexity, average case, and worst case. Okay, so let's find out the time complexity in all the cases for all the algorithms actually. So this matrix actually, there are many questions you will find out in GATE which are directly coming from this matrix itself. Okay, so you people can also share that thing. Can you tell me, okay, this thing you people tell me, what is the best case complexity of bubble sort? What is the best case complexity of bubble sort? I will also keep typing all this information, but let me first connect with you people. There may be, I think, some people may tell something different answer here. Different people may tell different answers here. I think so. So that's why I'm asking to you people. Can you tell me what is the best case time complexity of bubble sort? Can you tell me? Please write in the chat box. Please write in the chat box what is the best case time complexity of bubble sort. Everyone, please write everyone. Whatever you know, okay? Whatever you know, wrong or right doesn't matter. Just write uh, whatever you think that, okay, this is the complexity. So like digit already write that is order of n n power 2. Digit say n power 2. Okay, so we find out two answers from you people. One is order of n, one is n square. Okay, and both are right. Both you people are right. I will tell you how both can be right. How both can be right, I will tell you. Okay, and that is one of the most important question in interview also. Okay, we will discuss about this thing. We will discuss about this thing, how this can be n and how this can be n square. Okay, otherwise the average case complexity is n square. Worst case complexity of bubble sort is n square. Selection sort best case complexity is, okay, you people tell me, average case complexity is n square. I'm leaving it blank. Best case of selection sort, you please write. Meanwhile, I'm filling other. So average worst case complexity is also n square here. Fill this best also. What is the best of insertion sort also? Okay, and average case complexity is n square. Worst case complexity is n square. Merge sort is n log n. Best case complexity, average case complexity is also n log n. You please fill this entry. What is the worst case of bubble merge sort? Okay, best case complexity of quick sort is n log n. Average case complexity is also n log n. And you please fill the worst case complexity of quick sort also. Keep writing the name of the algorithm and its complexity. I'm leaving something blank, and you please try to keep write that. Okay, I'm leaving these blanks because my maximum questions are asked from this area, which is I'm leaving blank. Okay, so this is n log n, this is n log n, and this is also n log n. So heap sort best case, average case, and worst case complexity is n log n. Okay, let me check out about the selection sort first. In selection sort, I think you people are saying digit, and gate aspirant is saying n square, and that is right. So this is n square. And insertion sort, can you tell me insertion sort? So selection sort, you people tell me n square. Insertion sort best case, insertion sort best case complexity, please tell me. You people will tell me. Only 3 are left. What is the best case complexity of insertion sort? So gate aspirant says that that is order of n. Yes, that is right. And what is the worst case complexity of merge sort? Worst case complexity of merge sort. Worst case complexity of merge sort. What is the worst case complexity of merge sort? Can you tell me? Even you can check out on Google also. Okay, even nobody is watching you right now. So Ravish say that Ravish, welcome to the session. Welcome back. So that is Ravish say n log n. Very good. Ravish, can you tell me this also? So I have tough question for you. I believe you can solve it actually. So Mehak, welcome again to the session. And you are right. Are you talking about Mehak? Are you talking about worst case of quicksort? So Ravi says that is n square. Yes, Ravi, you are right. The worst case complexity of quicksort is n square. The worst case complexity of quicksort is n square. I was sure about this. Ravi will definitely give the right answer. I don't know, but I was sure. Okay, so these are the all the best average worst case complexity of these comparison based sorting algorithm I'm talking about. Non comparison based sorting algorithm, best case, average case and worst case, all the cases complexity is order of n. Order of n. Okay, for all the algorithm, for counting sort, for radix sort, for bucket sort, the complexity is order of n. Okay, the complexity is n, and here that is varying for all the cases. Okay, okay, now for my first question to you people, my first question now, first interview based question, first interview based question is that you can see here, these are comparison based sorting algorithm, these are non comparison based sorting algorithm. Non comparison based sorting algorithms is taking only order of n time in all the cases. We know this thing that n is less than n log n and n log n is less than n square. So this algorithm will take maximum time. This will take less than n square but more than n, and n will take less time as compared to these two. Okay, so we know this thing. So this sorting algorithm, I'm saying that in all the cases taking order of n time. Okay, and these algorithms, in if you check out the worst case, they are taking minimum. In worst case, what is the minimum time? In the worst case, what is the minimum time taken in the worst case? This is the gate question itself. What is the minimum time taken in the worst case? Okay, it's like what is the tightly upper bound of the worst case? That is actually n log n. N log n is the minimum time taken in the worst case. Okay, minimum time taken in the worst case is n log n. Okay, so what I'm saying that these algorithms in the worst case is taking n log n time, and even in average case also they are taking at least n log n time, at least even more than that, n square. And here only you can say okay, one or two algorithms are taking best case is n, otherwise all are taking more than n, or are taking more than n. Okay, so can you people tell me which algorithm is the best algorithm, comparison based or non comparison based? So my first question, which algorithm is good one, comparison based or non comparison based? You can write okay, only compare, you can write okay CB comparison based, or you can write NCB non comparison based. NCB short form we can write NCB non comparison based, or CB comparison based. So which algorithm is the good one to use, comparison based or non comparison based? And we have already discussed that the complexity of comparison based sorting algorithm is more than the complexity of non comparison based sorting algorithm. We have already discussed this thing, and gate aspirant still is saying that, comparison based sorting algorithm are better to use. Why can you tell me why you have to use the comparison based sorting algorithm? So this is the question actually, this is the interview based question actually. You are right actually, we use the, you are right, gate aspirant. We in practical application in industry, in practical application, most of the application I'm talking about, most of the, in most of the applications, most of the real life practical applications, we use comparison based sorting algorithms only. We use these algorithms only. We do not use these algorithms. Okay, even though they are taking less time, they are also can sort the elements. Okay, they are taking less time also. They are taking more time. They are taking more time, but still we use the comparison based sorting algorithm. And the reason is that, and the reason is that, does it say that I think CB, otherwise we studied NCB? In any language, while studying, we do not use NCB. See, it's not like that you do not study NCB. If they will be useful, then you need to study them. Okay, but I'm telling one thing that, okay, the question is, this question can anybody can ask you. Okay, like they are taking more time, they are taking less time, and you are, and these are algorithms still are used in industry. People are using these algorithms rather than these algorithms. Why? The reason is that these algorithms, non-comparison based algorithms, have limitations. Counting sort, radix sort, bucket sorts have some limitations. They limits the user. They limit the input. They say to user that, okay, don't give this input. Only give this type of input. Please don't give too much big numbers. Give only small numbers. So they are bounding. These people are bounding in this sorting algorithm, non-comparison based sorting algorithm. They bound the input. Bounding the input means they are bounding the user. And if there is a software who is bounding the user, that is one of the worst software. Actually, that is one of the worst software. We should not bound the user. They are bounding the user. Only give small inputs. Only give input of 3 digit or 4 digit or 5 digit. They're bounding. But radix sort is bounding like that. Counting sort is bounding. Okay, don't give too much large input. Okay, so these algorithms are behaving like that. So what I want to say that non-comparison based sorting algorithms have limits. Have their limits. They bound the input. They bound the input. Comparison based sorting algorithm do not bound the input. Do not bound the input. You can give any type of input. They will perform in this way only. Okay, they will take this much time only. Okay, they will behave uh, in the same way how they are behaving. But if we are not giving the input properly here, they may start taking, let's suppose, they will consume your all RAM. They will consume your all RAM. If you will give very large number to counting sort, if you are saying that, okay, you are talking to counting sort, I'm giving you two numbers. One is 1 lakh, one is 2 lakh. Can you tell me which number is greater, 1 lakh or 2 lakh? Then he will consume, this counting sort will consume your all RAM. That will consume your all RAM space to compare only two numbers. Why? Because you are giving too big number to this counting sort. Okay, so this is how these algorithms are working. If you will see the working, then you will find out that, okay, they are bounding the user. That's why they counting sort work better on small inputs only, on small inputs. That do not work better on large inputs, because that consume lots of space according to that. Okay, so in single line, if I tell you why we are using comparison based algorithm, not non-comparison, because these have limitations. They bound the input. They are saying to the user, don't give too much large input, give small input. Don't give 3-digit input, only give 2-digit input. Like that they are bounding. Okay, but they do not bound. Okay, so that's why practically we use these algorithms, because we cannot bound the user, Okay, okay, so we will start from comparison based sorting algorithm, and if we left with time, then we will cover these also. Okay, okay, so let's start with these algorithm, and let me take another question now. Okay, so here I will show you. Actually, bubble sort in best case take, let me tell you one thing first. Bubble sort take n square time in best case, but we can improve it to n. But we can improve it somehow. I will tell you how. Maybe you people already know. If you already know, please write in the chat box. Okay, we can improve the best case of bubble sort from n square to n. Okay, we can improve the bubble sort. We can do some modification in the code, and the complexity will reduce from n square to n. Okay, so now we are assuming that we have improved our code, and now the best case complexity of bubble sort is n. The best case complexity of bubble sort is n. Otherwise, if somebody asks you what is the best case complexity of bubble sort, you can say that, sir, the complexity is n square, but we can improve it to n. Then he will ask you how you can improve that. Then we will discuss about that how when we will talk about the bubble sort. But right now I have another interview question for you people. So right now the question is that, okay, the complexity of bubble sort is n, the complexity of selection sort is n square. These are matching. You can see this and this is same, worst case is also same, average case is same, worst case is same, but in best case bubble sort is taking order of n time, selection sort is taking order of n square time. So can you tell me which algorithm is the better one, bubble sort or selection sort? The question is which algorithm is better one I'm asking to you people. Again, this is an interview question. Which algorithm is the better one, bubble sort or selection sort? Bubble sort or selection sort? Please write in the chat box. Please write in the chat box. Keep writing whatever you know. Okay, keep writing whatever you know so that I can connect with you people, and our session will become more interesting actually. But you need to give the reason. If you are moving in opposite direction, you need to give the reason. You are saying selection sort is better, and why? Here we can see that bubble sort is taking n time, here that is taking n square time. So still you are saying why selection sort is better. Still you are saying selection sort is better. Why? Definitely then another question will come. Why selection sort is better? Praveen says that is bubble. So according to this scenario, Praveen is right. According to this scenario, because these are matching. Average case and worst case are matching. Okay. In the case of bubbles, best case, bubble sort is better than the selection sort, but still Mehak is saying that, gate aspirant is saying that selection sort is better. So I will ask you the question, why selection is better? Otherwise you people are right. Selection sort is better than the bubble sort. Note down, selection sort is better than the bubble sort. Even after this condition, we will prove this thing. Okay. But right now I am telling to you, yes, you are right. Selection sort is better than the bubble sort. If you know the reason, please write that. Yes, Praveen is asking, Praveen, your question is right, but bubble sort best case complexity is order of n. Still we are saying that selection sort is better. Why this is happening? Note down this question. After this slide, I'm moving to bubble sort and selection sort. There we will talk about this. Okay, when we will be knowing the working of bubble sort and selection sort, then you will be able to answer this question. So we have two questions I think with us. One is how we can improve the bubble sort, how we are improving the bubble sort from n square to n. Another question is, even though the complexity in best case bubble sort complexity is n and selection sort complexity n square, still we are saying that selection sort is better. Why? The question is why that selection sort is better. But that is right, selection sort is better than the bubble sort. Okay, so we have two questions with us. Okay, another question I'm taking another question, which I hope that is visible to you people. Which sorting algorithm is best if array is almost sorted? Okay, another question is, out of these sorting algorithm, these all algorithm, which sorting algorithm is which algorithm is the best algorithm? Which algorithm out of these algorithms, talking about comparison based sorting algorithm, I'm talking about out of these algorithms, which is the best algorithm when the array is almost sorted? Can you do anyone know about this? If the array is almost sorted means one or two elements are not sorted, all elements are sorted. Like maybe I'm writing, okay, maybe I'm writing 10, I'm giving you this number to sort, 10 in this sequence itself, 10, 20, 30, 40, 60, 50, okay, 70, 80, 90. So you can see that only these two numbers are not sorted, otherwise all elements are sorted. Okay, so that means almost sorted. So question is that If array is almost sorted, means one or two elements are not sorted only, then which of the algorithm is the best algorithm? This is again the interview question, and as well as already asked in 1 marks in the gate. So Praveen is asking why. Yeah, Praveen, I will come to your answer. Definitely you have to ask why, definitely. So Praveen says that, okay, bubble sort and insertion sort. Mehak says the insertion sort. Gate aspirant say that maybe insertion sort, and insertion sort is the right answer. Insertion sort is the right answer. Insertion sort actually is the best algorithm when array is almost sorted, not completely sorted but almost sorted. Okay, if array is completely sorted, then bubble sort can also work fine. If array is completely sorted, I'm talking about, see, listen to me properly. If array is completely sorted, if you're giving complete sort array to sort again, then bubble sort can also work fine. But if array is almost sorted, means one or two elements are not sorted, maybe one or two elements are not sorted, then bubble sort will behave worst. Then bubble sort again will give the n square time, that will again take the n square time, but insertion sort will take n time. Okay. Okay, so this is again can be a question. Okay, why this is happening? Why this is happening? If you know the working of these algorithms, then you will be knowing, okay, why this is happening. Okay, so now we have 2-3 questions with us. Now we can move on to these algorithms to clarify these questions. Okay, to clarify these interview questions, now we can start working on these algorithms. So this is the bubble sort, and bubble sort algorithm actually I have written here, and I have taken one example. Let me tell you how this algorithm is working. How bubble sort work? Let me tell you if you know the working, then you will be able to give the answer of every question. I'm going to tell you the logic only here, how bubble sort is working, how these two loops are actually working, how bubble sort is working. Very easy, very easy. Okay, even we can understand with its name itself, bubble sort. They are saying it's a bubble. Like bubble goes to the upside, here also the largest element will go to the upside. Okay, see how bubble sort work. Let me tell you. In bubble sort, what we do is we compare these two elements, and these two, 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 and these two. So we compare these two elements. Which one will be greater one? That will go to the right side. Which one will be greater one? That will go to the right side. So 80 will come here, 90 will come here. Again you will compare. Now 90 will 70. So the bigger one will come to the right side. Like bubble is going to the upside. Bubble always go to the upside. So 70 will come here, 90 will come here, 90 will come here, 60 will come here. I'm comparing all the nearby elements. Okay, so here 50 will come here, 90 will come here, 90 will come here, 40 will come here. So I'm comparing again these two elements. 90 will come here, 30 will come here. Comparing this and this, 20 will come here, 90 will come here. This and this, 90 will come here, 10 will come here. Now 5 and 90, 90 will come here, 5 will come here. Okay, so after one, this is the first pass. This is the one pass of bubble sort. Okay, this is the one pass. We need to perform this n minus 1 time. We need to perform this n minus 1 time. So after one pass, these are the elements we have: 80, 70, 60, 50, 40, 30, 20, 10, 5, and 90. These are the element sequence in our array after one pass. Okay, what happened after one pass? The largest elements goes to the right side, rightmost side. After one pass of the bubble sort, the largest element will go to the rightmost side. This is how bubble sort is working. This is not my algorithm. I do not develop this algorithm. Whoever developed this algorithm, he says that just compare near these two elements, these two, and what will happen? The largest at the end of this one pass, the largest element will reach at the end. Okay, and you can apply the same procedure now on n minus 1 elements. Again you can apply the same procedure. What? Compare these two. 70 will come here, 80 will come here. Again these two. 60 will come here, 80 will come here. So keep comparing. And what will happen? 80 will come here. Second largest element will now come here. All other element will be here. So what we will do? Again, we will apply the next pass on, we can say n minus 2 elements. N minus 2 elements. Same procedure we will apply. What is the procedure? Compare ith element, or you can jth element and j plus 1th element. Jth element and j plus 1th element. If jth element is greater than, j plus 1th element, then we will perform this swap. Then we are swapping the elements. If jth element is greater than j plus 1th element, we are performing swap. And this is one pass. And this is how many times we are performing this task. How many times we are performing? N minus, even I can say that, okay, n minus 1 time we are performing this task. Okay, n minus 1 time. So this is how bubble sort is working. Okay. Now, if we will see, let's go in more detail now. So let me tell you one thing. Now let's find out the complexity of these algorithm first. Okay, if we will be able to find out the complexity of bubble sort in detail, then that will be easy for us to find out for other algorithms also. Okay, so whenever you want to find out the complexity of any sorting algorithm, I'm talking about any sorting algorithm, comparison based sorting algorithm I'm talking about, then actually you check out two things. In that. What are those two things? First thing is number of swap operations you have performed. Second is number of comparisons you have performed. That's it. So what I'm repeating this thing again. Whenever somebody asks you the time complexity of any comparison based sorting algorithm, then you will check out how many swap operations you perform. Like here you swap 90 with 5, one swap, another swap, another swap. If you are performing the swap operation, how many swap operations you are performing, and how many comparison? Here you are comparing 90 with 80. You are comparing them. Which one is greater? You are comparing them. This is the comparison. This is the swap. So total number of comparison and swap you are performing, that decides actually what is the time complexity of that sorting algorithm. Okay, I'm talking in the context of every algorithm, every comparison based sorting algorithm. So let's talk about the bubble sort now. What is the time complexity of bubble sort? So time complexity of bubble sort we will find out by finding number of swap and number of comparisons. Okay, so you people tell me. Okay, now you people tell me. I'm talking about swap and comparison. So let's talk about swap first. Can you people tell me in one pass? Okay, I'm talking about only one pass, maybe in one pass, like you are comparing this with 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 this. How many number of comparisons you are performing? Let's suppose we have n elements. How many comparisons you are performing? Can you write in the chat box? Please write in the chat how many comparisons you are performing. Please write in the chat box. Everyone, please write in the chat box how many comparisons you are performing. So Praveen say n. So yes, that is approximately n, or you can say n minus 1 comparisons you are performing. Ravi say n minus 1. Yes. So n minus 1 comparison you are performing in one pass. This was the one pass only. One time you execute the internal loop. You executed the internal loop. Okay. And this thing you are doing n minus 1 time. Next time you will be having, you were having initially n elements. Then you will be having n minus 1 element in the next pass, because largest element will be at the right position, at the rightmost position. Then there will be n minus 2 elements in the next pass. Then there will be n minus 3 elements. So how many comparisons you will perform, how many swaps you will, comparisons you will perform? I can say that, okay, 1 plus 2 plus 3 plus so on up to n minus 2 plus n minus 1. Okay, okay, so these much comparisons you will perform, or even you can add, let's suppose, n also. Okay, one more comparison. I'm saying that, okay, I'm removing it from here, or starting from 2. Okay, so we get this series, and what is the value of this series is n into, approximately I'm talking about approximately, asymptotically. Okay, so n into n plus 1 divided by 2, this series is equal to this. And if you will solve this, what is the time complexity here? N into n, that will be n square. Approximately, again I'm talking about the complexity. We always find out the complexity approximately. Okay, so the complexity, so if somebody asks you what is the what are the number of comparisons you are performing in bubble sort, in worst case, that will be n square. If worst case we are talking about number of comparisons asymptotically, I have to say more correctly, asymptotically means approximately. I'm not taking exact, we are taking approximately, that is n square comparisons we are performing. Okay, n square comparison we are performing. I hope this is clear. If any doubt in this, you please ask me, because this thing is going to repeat again and again, these type of things. Otherwise, can you tell me what will be the I can write here itself, comparisons we are finding. In the worst case, we already find out, that is n square. Can you tell me what will be the number of comparison in best case? Number of comparison itself in the best case. In the best case, number of comparisons. Even before that, I can ask you one more question. There are many questions we can ask actually from this sorting algorithm. That's why people like to ask the question from here, and these are very interesting questions. Another question, before asking this question itself, you are saying that Praveen saying that again n square. I think Praveen is saying that, Praveen is right actually. In best case, that will again take n square. In best case, that will again take n square. So even before this question, I can ask another question also. What is the question? What do you mean by best case? What do you mean by best case? So please note, best case is different than best case complexity. Both the terms are different. Best case complexity is this. But what is best case? So let me give you the example of this. The best case of bubble sort is when array is already sorted. When array is already sorted. If array is already sorted, that is the best case of bubble sort. And I ask you another question. What is the best case complexity? What is the best case? If I'm saying I'm giving you the best case. If I'm saying I'm giving you the best case, I'm saying that I'm giving you the sorted elements. In the case of bubble sort, I'm talking about. In the case of bubble sort, best case is sorted element I'm giving. Okay. So if I'm giving you sorted elements, so what is the time complexity? You are saying that still that is n square. Still that will take n, that how much time that will take? N square. You are saying that that is n square. Okay. And here CS Guru says that that is n. That is n. That is n. So even if you are saying n, how that is n, you can write in the chat box. Otherwise, this is right, but we can improve it to this. Again, the same question is coming, which was coming earlier. So this is right. This much comparisons we need, but we can improve it to this. Okay, how we can improve it to this? How we can reduce the number of comparison to this? Okay, modified bubble. Yes, you are right that we are modifying the bubble now. So before modifying it, let me modify it here, and you can write that also, how we can modify. So we are covering now two questions. The question was, okay, how we are improving bubble sort complexity from n square to n. So actually, number of comparisons is also helping us to find out the complexity itself. If we can reduce this, we can reduce the overall complexity also. We can reduce the overall complexity also. How we can reduce that? Let me write the code for that. So I will set, okay, we can set a flag here. Actually, we can set a flag here. So even we can set here if we want to come out. Okay, flag variable. Flag is a variable. I'm setting that value to 0. I'm taking a variable. Okay, flag is a variable. I'm setting its value to 0. Okay, and this is I'm setting in the outer loop. After coming into the internal loop, into the internal loop, if I'm performing any swap, in the if condition, what I can do, I can write one more statement here. In the if condition, I'm writing flag plus plus. I'm incrementing the flag. Okay, I'm incrementing the flag. And after coming out of this loop, actually, what I can do is I can set a if condition. If this is inside the outer loop, but outside the internal loop. If flag value is equal to 1, if that is incremented to 1, then what we can do is we can return from here. We can even return, or we can break the loop. Okay, so this is how we are modifying the code. Okay, okay, what modification we are making now? Let's try to understand that thing. Okay, you people tell me. Okay, one question. I'm asking you one question. You need to think over it. I'm giving you sorted elements. That is the best case, actually. That is the best case of bubble sort. I'm giving you sorted elements 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, sorted elements I give you, and then I'm saying that you please compare them. Okay, so I'm giving you sorted elements. Okay, 10, 20, 30, 40, and 50. Okay, I'm saying that, okay, apply the bubble sort on this. What you will do, you will compare these two elements, then these two, then these two, then these two. Okay, you are doing like that. So I'm now asking you to a question now. I'm giving you sorted elements. And how many swap operations you will perform in that? How many swaps will be there if the elements are already sorted? How many swap will be there in the first pass, if I ask you? In the first pass of the algorithm, how many swap operations you will perform if I'm providing you the sorted elements? How many swap operations you will perform? So gate aspirants say that only one pass, 0 swaps. There will be 0 swap. Okay, gate aspirant is saying that if I'm providing you the sorted element, there will be 0 swap. Okay, I'm modifying the question now. I'm saying that if I have the sorted elements, if I already have the sorted elements, then I'm sure that then I can give guarantee. Okay, there will be 0 swap. Or we can reverse this also. If there will be 0 swap, then I can guarantee the array is already sorted. So I'm making the second statement is very important. In the first pass of the bubble sort, if no swap occur of any element in first pass of the bubble sort, then I can give you guarantee that the array is already sorted. We do not need to go for other passes. Even in first pass, we can predict the array is already sorted if no swap is occur. So this is the statement we can make. So if you are not agree with this, you can write that thing. Okay. Otherwise, if we are not making even a single swap, if we are making 0 swap, then we are sure that the array is already sorted. And this is what we are doing. We are setting a flag value to 0, and we are setting it, incrementing it if swap is occurring. Okay, if we are incrementing it if swap is occurring. If swap is not occurring, then flag value will be 0 remain. That will be zero remain. That will be zero remain, and we will come out of the outer loop also. We will come out of the outer loop. So how many times this loop is executed? How many times this algorithm is executed? Only one time this internal loop is executed. This internal loop is executed completely one time. Only one pass is executed. One pass is executed. If you are executing one pass, if you are executing one pass, then number of comparisons you already tell me that will be n minus 1. If you are executing one pass only, one pass in first pass only, number of comparison will be n. In all the passes, that will be n square. In all the passes that will be n square. But so if we are using the flag, if we are checking that what we how we can modify this, if we can set a flag, we can increment the flag value, and we can check if any swap occur or not. If no swap occur, then we can come out of the outer loop also. Okay, after one pass we find out that no swap occur, nothing occur, no swap occur, then we can what we can do, we can break out and we can just simply come out, and we can simply print that okay, the array is already sorted. The array is already sorted. We do not need to sort it because we are sure. How we are sure? Because no swap occur in the first pass. If no swap is occurring in the first pass, then we are sure that okay, array is already sorted and we can come out of the outer loop also. So this algorithm is now executed. Outer loop is executed one time, and this one time means for I value 0 only. For I value 0 only, outer loop is executed, and internal loop is executed completely from 0 to n minus 1. Okay, this much the internal loop is executed. So one time completely this executed, and this is executed only for I value 0. Okay, so the complexity is how much? N. How much complexity is there? N. So this is how you can improve the best case complexity. Again, I'm talking about best case when array is already sorted. When array is already sorted, you can use the flag. After using the flag, you can come out of the come out of the outer loop by setting the by incrementing the flag value here. If you find out that okay, flag value is still 0, you are sure that no swap is occur, so no need of further going through all the passes. After one pass, you will come out. In one pass, the complexity will be n. In one pass, the complexity will be n. Okay, so the best case we can say that, so in the best case we can say that the complexity is n. What is the complexity? Number of comparison you are performing is asymptotically, again I will say, that is n, and worst case that is n square. Okay, so these are the number of comparisons. These are number of comparison. If that is some doubt is there, no problem, we will discuss the same thing approximately with the help of swap. Can you people tell me, can you please write in the chat box, can you please write in the chat box how many, what is the worst case? In worst case, how many swap operations will be there? In worst case, how many swap operations will be there? Can you write that? What will be the worst case? Somebody asks you what is the worst case of bubble sort? If array is sorted in decreasing order, like 90, 80, 60, 70, 40, and so on, and you want to sort it in increasing order. Okay, so if that is in decreasing order, like 90, 80, and 60, so that is the worst case. That is the worst case actually. And I'm talking you in how many swaps will be there. How many swaps will be there? That will be, Prabin says that is n square. There, yes, that is similar as the comparison, because if 90, 80, 70, 60, that is just like that. Every time there will be swap. 90 will come here, 80 will come here. Like 80 will come here, 70 will come here. Every time swap is occurring. Every time. So n minus 1 time swap will occur in one pass. We have approximately n passes. So the total time will be n square. Just like this. And 1 plus 2 plus 3 plus up to n, and total will be n square swaps. And how many swaps will be there in the case of best case? Best case number of swaps, please write. Please keep replying. Please keep thinking and keep replying. Otherwise, this thing will repeat again and again for all the algorithms actually. Okay, so maybe we are taking little extra time in the bubble sort. Maybe we may find little difficulty here. Don't worry, we will repeat this thing again and again. Don't worry. So number of swap I'm asking now. Number of swap in the case of best case, please let me know. This is the last thing I'm asking. So Ravi says, Praveen says that is 0. You people are right. So in the best case, the array is already sorted. So if array is already sorted, we are not performing any swap. We are not going in this if statement. We are not performing any swap if array is already sorted. We know this thing. And now if somebody asks you what is the time complexity of bubble sort, then you can write like this. Let me make some space here. So let me write it. So that time complexity of bubble sort is number of comparisons you perform plus number of swap operations you perform. So if we talk about the worst case complexity, worst case, that is how much? N square plus n square, n square plus n square, that is 2n square, and again asymptotically that is n square. Okay, asymptotically is n square. This is the worst case. And what about the best case? So in best case, that is n plus 0. Number of comparison is n, number of swap is 0. So total is asymptotically n. So this is the time how we can find the time complexity of bubble sort and bubble sort in best, worst case and best case. Okay, and this is how we can improve the best case complexity by using a flag. Because what is the principle? Actually they will ask about the principle. What is the principle? Because we know that if there is no swap occurring in first pass, in very first pass, if no swap is occurring, then we are sure array is already sorted. Then why we are going through all the passes? Let's break out of the loop, outer loop. Let's break out of the outer loop and improve the algorithm. And in the best case, we can reduce the complexity to n only. And the number of comparison will be n, number of swap will be 0. So this is one thing. We have covered one question also, which we left earlier. So another question was, okay, I was saying that selection sort is better than bubble sort, although the best case complexity of bubble sort is n, and selection sort best case complexity is n square. So we will come to that question now. Here any doubt you can ask me. Here any doubt, please don't hesitate to ask me. Simply post the question. If even I am turning the slide, still you can ask the question from here. Okay. Okay. So before moving on, let me take some more important questions from here itself. So we already know how many swap operations you. These are also actually interview based question. Actually, how many swap operations are there in bubble sort? So you already know in worst case, that is actually n square, you know this thing, and in the best case that is actually 0. You already tell me this thing. Okay. And how many comparisons operations are there in the bubble sort? You already tell me. In the worst case, the comparisons are n square, and in the best case, number of comparisons will be, you can say, okay, either you can say n minus 1. Okay, asymptotically that is n. Asymptotically that is n. Okay, so we already know the answer of these questions. If any doubt you can ask me, otherwise we are moving to the selection sort now. So let me tell you how selection sort work. So let's suppose we have some these elements, same element I have taken. So in selection sort, that is very easy actually. We assume that the first element is the smallest element. In selection sort, we found the smallest element first. In bubble sort, we were finding the largest element. Largest element was going to the rightmost side, then second largest, then third largest, then fourth largest, and so on. We were moving from the back side. Okay, and in selection sort, we will find out the smallest element first. First smallest, then second smallest, then third smallest, and fourth smallest, and so on. How we are finding? Simple. So let me give indexing to these elements. These are in array, let's suppose. Okay, what we are doing here, I will maintain a variable, let's suppose min. I'm assuming that the element at 0th position is the minimum. Means of this our initial first element is actually 0th element. I have to say 0th element is the minimum element. I'm assuming that before starting the algorithm. Okay, and after that, what I will do, I will compare this minimum element actually with every other element. with every other element I will keep comparing. And if I find out the smaller element than this, then I will change. I will say that okay, now this is the minimum. Now this is the minimum. Okay, let's do that. So initially min is at the 0th position. Okay, we compare this with this element. We find out that okay, this 80 is smaller than this. Then I will say that the element at the first position is the minimum now. Element at the first position is the minimum. Then I compare with the next element, the minimum element. The minimum element now at this time is at the one position. So I see that 70 is less than 80. Okay, I will say that no, the minimum element is at the second position. Okay, I will keep comparing with every element. Now I will compare the element at second position with the 60, and that this is greater than this. So minimum is now is 3. Till now the minimum element is this position, at this position. Now I compare with this 5. So I find out that the element at third position is greater than this element. So I will say that no, I find smaller than you. I find smaller than you, which is at fourth position. Okay. Then I keep comparing with all the elements. Then I compare with 40. Then I see that the element at fourth position is already smaller than 40. So I will say that no, that I have already the position of the element which is smaller one. So I compare with the next one. 4 is this 5 is still less than 30. So this is still less than 20. 5 is still less than 10. 5 is still less than 50. So after first pass, this was the first pass. That's it. After first pass, I find out the position of the smallest element. I find out the position of the smallest element. Then what I will do? I will do one swap operation. What I will do? I will swap this element with the very first element. Okay, yeah, 0th element you can say. So 5 will come here, 90 will come here. 5 will come here, 90 will come here. Okay, in array we will be having 5 here, 80, 70, 60, 90, 40, 30, 20, 10, and 50. Okay, so after first pass, smallest element reach to the starting. After first pass, smallest element reach to the starting. And again, we will perform the same procedure. Now we will assume that this is the smallest element. Okay, and perform the same operation here. We will find out the second smallest. Okay, then we will perform sub again the same procedure on n minus 2 elements, then n minus 3, n minus 4. That's it. This is selection sort work. This is how selection sort works. That's it. And this is what we are doing here itself. We are saying that okay, the element at 0th position is now minimum, and we are checking now. What we are doing here, we are executing this internal loop. We are taking this internal loop. This is our internal loop, and here we are checking okay, if the element at minimum position is greater than the current position. If that is greater than, then I will say that okay, this is jth element is more smaller than you. So I will store the index. See, I'm storing the index of the smallest element in the min. Okay, I will keep doing this thing in one pass. So this was the one pass. Internal loop is actually one pass, and this outer loop is executing for n minus 1 passes. That is executing for n minus 1 passes. And after coming out of internal loop, we are performing a swap. After coming out of one pass, we are performing this swap. Okay, we are swapping 5 with 90. 5 with 90. Okay, that's it about the selection sort. Now let me ask you some important questions. From selection sort. So first is, how many swap operations are there in the selection sort? Can you tell me how many swap operations? How many swap operations you will perform in the best case? Okay, in the best case, how many swap operations you will perform? And also in the worst case, you need to tell. Okay, first tell about the best case. In best case, how many swaps you will perform? And can you tell me how many swap you will perform in the worst case? In the worst case, how many swaps will be there? In the worst case, Okay, I think Praveen is talking that okay. In the best case, we are performing 0 swap, and the worst case we are performing n. Okay, actually we are performing n swap in the worst case, and we are performing n swap itself in the best case also. In best case also we are performing n swap, and in the worst case also we are performing n swap here actually. So worst case, that will be clear, I think. Why we are performing in the worst case n swap? See, for after every pass, after one pass, how many swap we are performing in one pass? In one pass, we are performing only one swap. In one pass, we are performing only one swap. We we are performing comparisons. We are comparing. We may compare n times. We are comparing n time. We are comparing with all the elements. We are comparing with all the elements. Yes, number of comparisons are n. Number of comparisons are approximately n or n minus 1, you can say. Okay, but in one pass, the swap was one only. The swap was one. So this was for one pass. In one pass, you are performing one swap. In n passes, and there will be n passes, or you can say n minus 1 passes. So there will be n minus 1 swap. Asymptotically, n swaps will be there. Okay, that is the worst case. And but this is also going to be the case of best case also. See, in best case, Praveen is saying that the number of swap will be 0. He think that okay, if the array is already sorted, he think like that maybe, and that anybody can think like this only. Okay, anybody can think like this. So if array is like already sorted, 50, 60, 70, 80, okay, and we are assuming that the minimum element is this element. Okay, so at zeroth position, okay, and when I will compare 10 with every other element, when I will compare 10 with every other element, then I will say that the minimum element at the 0th position itself, if I'm giving the elements at sorted elements, giving as an input, then I will find out that in first pass, my initial element itself is the sorted, is the minimum element. Okay, then, but still, Praveen, still we are performing this operation. Still we are performing this operation. After coming out of this loop, after coming out of this loop, we are still swapping. Then you will ask, sir, to whom we are swapping? Then we can say that we are swapping 10 with 10. We are swapping 10 with 10. Then after first pass, we will swap 20 with 20. We are swapping a of 0 with actually a of 0 here. And here a of 1 with a of 1. We will keep performing this operation. Okay, so the number of swap will be, in the best case also, that will be n. The number of swap will be n. Yes, that to itself. And that's the reason why in the best case also that is taking n. Okay, so you already tell me now. Number of swap, let me write here. Let me write in the best case and worst case, you tell me n and n. Okay, and number of comparison, how many comparison we will perform in the best case and worst case? Number of comparison, can you tell me? Can you people please share the in the best case first? Keep trying. Right or wrong doesn't matter. Keep trying. Right or wrong doesn't matter. Please let me know what will be the best case number of comparisons you need to perform. Number of comparison. See, in the best case, even you are comparing with all the elements. You are comparing with all the elements in one pass. Another pass, you will do the same thing. So it will be like this: 1 plus 2 plus this much number of comparison will be there. Okay, and this is again n into n plus 1 divided by 2, which is again order of n square. Asymptotically, I'm writing here. Okay, so n square number of comparison will be there in the best case. In the worst case, that will be n square. Okay, then what is the time complexity of selection sort? So in worst case, that will be this much. That will be n plus n square. That is asymptotically n square. In best case, how much? N plus n square. That is still n square. So, so now let's come to our question. The question was earlier, which I asked, was that we say that out of selection sort and bubble sort, which algorithm is the better one? And some of you were saying that selection sort is better one. And what is the reason? Now, can you tell me what is the reason why selection sort is better one? What is the reason why selection sort is better one? Yes, because Gates parents say that best case and comparison. Okay, because the reason is that number of swap you are performing, and in all the cases, in best and average and worst case, you are performing how many swaps operation, how many swap operation you are performing? N. You're performing only n swap operations. Okay, but there in bubble sort, in bubble sort, every time you need to perform n square. Except the best case, only one case is there in bubble sort. Only one case is there. The element is completely sorted. The element is completely sorted. That is the only case where there will be zero swap. Otherwise, even one element is not sorted. Then again, the number of swap will increase actually in that. Okay, because one element will keep swapping with all the elements. Let's suppose largest element is at the front, then that will keep bubbling up to the end. Okay, so this is the reason. We can say that the answer will be because the number of swap in selection sort is n, and in bubble sort that is n square. So that's why selection sort is better than the bubble sort. Although asymptotically this seems that in best case bubble sort is better than the selection sort, but in actual applications where we cannot assume that maximum time you will find out the unsorted elements. Maximum time, maybe one or two time, maybe I don't know, somebody will give you the element to sort, somebody will give you sorted element to sort. I don't know who will give you the sorted element to sort again. So in that case, that can happen, that okay, number of swap can be zero. Otherwise, every time number of swap will be very less. N square is very, very large as compared to n when n tends to infinity. So that's why this is the big difference. This is not a small difference. This is a big difference. N square is having the big difference because we find the complexity for large input. How much large? N tends to infinity. When you will put the large value in n, then this value will be very, very big compared to this one. So that's why selection sort is better than the bubble sort, because number of swaps are here n and there is n square. Why comparison is n square if array is already sorted? Why comparison is n square? Okay, so here the elements were sorted already, but this was, we need see, okay, gate aspirant, we give this input. Okay, हमने ये input दी उसको, अभी अपने को नहीं पता ये एलिमेंट सॉर्टेड है, एल्गोरिथम को नहीं पता है ये एलिमेंट सॉर्टेड है, उसको नहीं पता है ये एलिमेंट सॉर्टेड है, उसको नहीं पता है। उसको तो कैसे पता लगेगा? उसको तो कंपैरिजन के बाद ही पता लगेगा, उसको तो सभी एलिमेंट से कंपेयर करके ही बाद ही पता लगेगा। ये ऐसा ही है जैसे एक क्लास में बच्चे बैठे हैं और मेरे को फाइंड आउट करना है कि भाई किस बच्चे की एज सबसे मिनिमम है, किस बच्चे की एज सबसे मिनिमम है। देन आई आस्क टू फर्स्ट स्टूडेंट, व्हाट इज योर एज? He says that my age is 20. Another one says that my age is 21. Another one says that my age is 18. Then I ask to n minus 1 students, and I ask to n minus 1 student. Am I sure that after asking to n minus 1 student, am I sure that okay, I know the age of minimum age of a student? Minimum age? No, I need to ask to all the student. I need to ask to all the student. Okay, even I need to ask to the last student also. That may be a girl, that may say that I'm only 15-year-old. Okay, that may be lying itself, but she can say like that. So she will be having the minimum age. Okay, so I need to compare with all the element before saying that okay, this is the minimum element, although that is minimum element. But I don't know initially, if somebody give me the input, algorithm don't know, This is sorted. We know, we are standing here, we know that thing. Okay. Okay, so you know this thing, both of these question, number of comparison, number of swap in selection sort, and that question is also clear why selection sort is better than bubble sort. Now let's move to the insertion sort, and there was another question. If array is almost sorted, then selection sort is the best sorting algorithm. Okay, we will take this question. Before that, let's see how insertion sort works. So in insertion sort, see how insertion sort work. Very easy. Compare first two elements. If second element is smaller than first one, then swap. But 20 is greater, then we will not swap. छोटा एलिमेंट लेफ्ट में जाता रहेगा, बड़ा एलिमेंट राइट में रहेगा, बस सिंपल. फिर we will then after that we will pick the third element, compare with second first. Is this greater than this? 50 is greater? Yes. अगर बड़ा है तो वो राइट में ही रहेगा, छोटा हुआ तो लेफ्ट में आ जाएगा स्वैप होके. Now we will compare 30 with 50. 30 is smaller than 50. Now we will perform swap. See, we will not stop here itself. We will keep comparing till this number will become larger than the left side number. Okay. Now we will again compare. We compare with 30 with 20. So 30 is now greater. Okay. Larger number should be at the right hand side. So now we will pick the next element, compare with 30. 60 is larger. Sorry, not with 30. 30 is now 50. But 60 is still greater than 50. 60 is still greater than 50. No need of anything. So now again 70 is greater than 60. So compare 5. 5 is less than 70. So we will perform swap here. So 5 will come here, 70 will come here. Although let me tell you, this will not perform the swap. Here we perform the shifting, we say that. Okay. Okay. So let's do like this only. Okay. Okay. So 5 with 60, 5 will come here, 60 will come here. We compare 5 with 60, 5 will come here, 60 will come here. Again compare with, I will keep comparing till the first element, until unless I find out that, okay, this is not the smallest one. Okay. 5 with 50, 5 will come here, 50 will come here. 5 with 30, 5 will come here, 30 will come here. बड़ा एलिमेंट राइट में जाता रहेगा, छोटा एलिमेंट लेफ्ट में आता रहेगा. ये 5 छोटा है तो वो लेफ्ट में जाएगा ही जाएगा, उसको कोई नहीं रोक सकता. 5 will come here, 20 will come here. 5 will come here, 10 will come here. So after sorting, that's it. This is complete insertion sort. This is complete insertion sort. Okay. This was the first pass, you can say. This is the second, this is the third, this is the fourth, fifth, and last pass. It's like that. Okay. Otherwise, this is the complete insertion sort. Now after sorting, we have these elements in our array. See, 5, 10, 20, then 30, then 50, then 60, then 70. So our array is sorted. Our array is sorted now. Okay. So this is how insertion sort works. Okay. Okay. Let me tell you one more thing now. Let me tell you one more thing. Rather than swap here, rather than swapping the elements, like I was swapping 5 with 70, then 5 with 50, like that. Okay. We can do like this also. That will not make any impact. Otherwise, the actual algorithm, they perform the shifting rather than swapping. They perform the shifting. So what is shifting? That is same as this thing only, but let me tell you what they are doing. In, let's suppose we want to we are checking for this element, let's suppose now. Okay, then I was swapping these numbers, but actually we will not swap these numbers. We will see, okay, this is less than this. Okay, then I will compare with this also. I'm not swapping, I'm just finding out. Okay, right now, to from how many numbers this number is less, I'm finding this thing. Okay, so we compare 5 with 60. 5 is also smaller than 60. Then again compare. 5 is smaller than 30. Yes. 5 is smaller than 50. Yes. 5 is smaller than 20. Yes. 5 is smaller than 10. Yes. So I reach here. I say that, okay, I find out the position where 5 should be. 5 should be at first position, this position. What I will do, I will shift. I will shift 70 here, 60 here, 30 here, like that. I will shift. And then 10 here, and there will be space. I will insert 5. Okay. So this is known as shifting. क्या कर रहे हैं इसके अंदर हम क्या कर रहे हैं? सिंपल है, हम उस एलिमेंट की पोजीशन ढूंढ रहे हैं, वो कहाँ पे जाके उसको शिफ्ट होना है, और हम बाकी एलिमेंट को शिफ्ट किए जा रहे हैं. ओके, this will behave just like a swapping only, otherwise this will behave like a swapping only. Okay, but there remain some questions in exam, they talk about shifting, that's why I tell you about shifting. Okay, otherwise both are doing the same thing. उसमें भी क्या कर रहे थे, हम कंपेयर कर रहे थे, साथ के साथ स्वैप कर देते, साथ के साथ साथ के साथ साथ के साथ साथ के साथ. पर यहाँ पर हम क्या कर रहे हैं, हम कह रहे हैं अभी हम उसकी पोजीशन फाइंड आउट कर रहे हैं, वो कहाँ पे स्टोर होगा, हम उसकी पोजीशन फाइंड आउट कर रहे हैं, और पोजीशन फाइंड आउट करने के बाद फिर लास्ट में हम उसको वहां पे शिफ्ट कर दे रहे हैं. ओके, और बाकी एलिमेंट को भी हम शिफ्ट कर दे रहे हैं, तो शिफ्ट ऑपरेशन बोल दिया. एक एक सभी एलिमेंट को एक एक राइट साइड में शिफ्ट कर देंगे. ओके, so this is how insertion sort work, that's it. Okay, this is how insertion sort works. And let's take some question from here. So the question is, how many shift operations are there in insertion sort in best case? So let's see the shift operations, which is something same as swap operations. Okay, no need to confuse. So another one is comparison. So the question is, how many shift operations we are performing in best case? In best case, so the best case, in best case, how many shift operations we are performing? Let me tell you the best case of insertion sort when array is already sorted. When array is already sorted, then that will be the best case of insertion sort. Okay, let me tell you one more thing. If you are moving on here, let me tell you one more thing. This is not always true that if array is already sorted, that doesn't mean that will always be the best case. If array is already sorted, that doesn't mean that will always will be the best case of every algorithm. No, there can be algorithm which is if the array is already sorted, that is the worst case of that algorithm. Can you tell me the name of that algorithm, anyone? If array is already sorted, we are giving sorted elements, and he is behaving in worst. He behaving worst for that. That will be the worst case for that. He will take the maximum time to sort that. I'm giving a sorted element to a algorithm to sort the element. I'm giving sorted elements, and he is behaving in the worst. Okay, he is behaving worst. Can you tell me the name of that algorithm? Anyone can tell me the name of that algorithm? If we give the element in sorted order, still that is behaving in the worst. That is behaving worst in that case. That will be the worst case of that algorithm, not bubble sort. Bubble sort will take order of n time. If I will give sorted elements, then bubble sort will take n time even, not bubble sort. Anyone else? So which algorithm is will take maximum time? You can say that will the which algorithm worst case is the if the elements are sorted. So that is the quick sort. That is the quick sort. If you will give the sorted element to quick sort will behave the worst. Okay, do you know, let me ask you one more question. These are all interview question actually. So let me ask you one more question. Out of all the comparison based sorting algorithm, which sorting algorithm is the best one? Which sorting algorithm is the best one? Can you tell me? I have write some of like bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. Even you know the time complexity also, all of them, the time complexity of all of them. Can you tell me which is the best sorting algorithm in real life applications? If we talk about if for real application, industrial application, GATE aspirants say that is the quick sort. Yes, quick sort is the best sorting algorithm out of all the sorting algorithm. Otherwise, you can claim whoever is developed the quick sort, you can put a case on him. You can say, why you write the name quick if you are not quick? That is the best algorithm. We will take this question, why we are saying that quick sort is the best sorting algorithm, even though that is, if you will check out, even though that is taking n square time in the worst case, even though quick sort is taking n square time, still I'm saying that quick sort is the best sorting algorithm out of all the comparison based sorting algorithm. Still I'm, so we will talk about that in the quick sort. So right now, you people tell me, in the best case, number of shift you need to perform. And I'm telling you, the best case is when array is sorted. Okay, like 10. I'm giving you these elements. Okay, and you need to apply the insertion sort. You will compare this with this. No swap, no shift. If there will be no swap, there will be no shift. Compare this with this. This is greater than this. No swap. This will compare this and this. No swap. This with this. No swap. This with this. No swap. No comparison. No shift. Okay. So can you tell me how many shift operations or swap operations you will perform in the best case of insertion sort? How many shift operations you will perform? Can you tell me? Anyone? Please answer the question. That is 0. Yes, you are right. You are performing 0 shift operation if array is already sorted, completely sorted. Okay. And in worst case, how many shift operation you will perform? When array is sorted in decreasing order. Okay. Then every time like this, then every time you need to perform one shift. 90 will come here, 80 will go here. Here two shift operations. Actually 70 will come here, 90 will shift here, 80 will shift here, and 70 will come here. So in this case, 3 shift. This, and 60 will go here. In this case, 4. So 1 plus 2 plus 3 plus and so on. And how much is this? We know n square. How much is this? N square. So in worst case, there will be n square shift operation. Number of comparisons, number of comparison in best case, you can write in the chat box. Otherwise, in worst case, number of comparison is same as this one. We need to compare 50 with this also, this also, this also, this also. So we are comparing with 1 plus 2 plus this much number of comparisons we are making. That is again n square in worst case. In best case, you can write number of comparisons you are making. In best case, you can write that, and that will be actually, in best case, number of comparison will be n. Why? In best case, you are comparing this element with this element one time only, this with this one time, with this. You're not comparing 40 with 20 and 10. You're comparing 40 with 30 only. You're comparing 50 with 40 only, because that is already greater than 40. You do not need to compare with these elements, because we are sure that in insertion sort, whenever we are moving from left to right, we will keep sorting the elements. Okay, जैसे जैसे हम ये एक एक एलिमेंट को कंपेयर करते रहेंगे, we will keep generating the already sorted elements. Okay, we will keep generating the sorted array. So we need to compare only one comparison for n elements, n minus 1 comparison. So asymptotically n. So what is the time complexity of insertion sort? Time complexity of insertion sort is, in best case, that is 0 plus n, that is order of n. And in worst case, that is n square plus n square, that is asymptotically again n square. Okay, now, okay, this is the time complexity now. Now my one question is that, if the array is almost sorted means 1 or 2 elements are not sorted. Let's suppose like this. I have element 10, 20, 30, 40, 50. Let's suppose one element I have here at the end. So in this case, actually, you will compare this with this, this with this, this with this, this with this. No swap will be occur, no shifting will be occur. Okay, but in this case, this will compare with all of them, and all will shift actually. Okay, so number of comparison is n, and number of shift is also n. Okay, so total number of how many operations you perform. So number of comparisons and shift That is the complexity of any algorithm. Comparison is n, shift is n. Okay, total is 2n. So that is again n actually. Asymptotically that is n. And for all other operation, because this was the best case, here, because these are already sorted. So for all other operations, we know that best case complexity is n. So all these elements will take n time, and this element will also take n time to get sort. So total time, again you can add this and this. So n plus again n is 2n, that is order of n. Okay, so what I am trying to tell you is that if array is almost sorted, even one or two elements are not sorted, still insertion sort take how much time? Order of n time. But bubble sort will take again n square, because in bubble sort we are working on the principle that if no element is, if no swap is occurring, then only we will come out of the loop. Okay, so bubble sort behave on that principle actually. So that's why, and here actually we are saying that okay, even two elements are not sorted, that will be 3. If 3 elements are not sorted, that will be 4. So this is a constant number we can remove. That is the constant number we can remove actually. Okay, so this will take n time, even though some of the elements are not sorted. All other elements are sorted, but only some of the elements are not sorted. Then insertion sort is the best sorting algorithm. So another, this is the gate quotient itself that is written here now. We already talked about the shift operations and comparisons, and we already covered the previous question also. The another question is, see, the question is like this. Let me tell you, these are all important questions actually. That's why I put it here. Another question is like that. Okay. Let's suppose. Up to here we have sorted the elements. Okay. We know one thing. जैसे जैसे हम कंपेयर करते जा रहे हैं, हमारा लेफ्ट साइड एरे सॉर्ट होता जा रहा है. हर पास के साथ लेफ्ट साइड एरे हमारा सॉर्ट होता जा रहा है, ये हमें पता है. अब इतना लेट्स सपोज इतना एरे आपका सॉर्ट हो चुका है. ओके, ये एक एलिमेंट बचा हुआ है. हम कैसे इंसर्शन सॉर्ट फॉर्म करते हैं? हम इसको ना सबसे कंपेयर कर रहे थे, इससे भी. हम लीनियर सर्च अप्लाई कर रहे थे यहां पर. कौन सी सर्च? लीनियर सर्च. ओके, लीनियर सर्च में आप एक एक एलिमेंट से कंपेयर करते हो, तब आप डिसाइड करते हो ये एलिमेंट किससे छोटा है, इसकी क्या पोजीशन होगी. जैसे कि हम यहाँ पे आके रुक जाएंगे. ओके, कि भाई ये 20 से बड़ा है, तो इसकी पोजीशन उसकी पोजीशन क्या हो जाएगी? आफ्टर 20. दिस विल कम आफ्टर 20. सो इन प्लेस ऑफ 30 दैट विल कम. तो हमें ये शिफ्ट करने पड़ेंगे यहां तक बस. तो मैं रिपीट कर रहा हूं, मैं एक बोल रहा हूं, यहां तक हम लेट्स सपोज एरे सॉर्टेड है हमारा, ये एलिमेंट है जो हमें प्लेस करना है. तो हम यूजुअली क्या कर रहे हैं इसमें, ये एल्गोरिथम क्या कर रहा है, ये एक एक एलिमेंट से कंपेयर कर रहा है. हर एलिमेंट से कंपेयर करने के बाद डिसाइड कर रहा है कि भाई इसकी पोजीशन क्या होगी, ये किस पोजीशन पे आएगा, और उस अकॉर्डिंग ये शिफ्टिंग कर दे रहा है. ठीक है, ये ऐसे काम कर रहा है. पर ये क्या बोल रहा है अपने को क्वेश्चन, ये ही इज आस्किंग दैट कैन वी अप्लाई द बाइनरी सर्च हियर rather than linearly searching the position of this element. Can we apply the binary search to find out the exact position of the element? Can we apply the binary search over it? Can we apply binary search? Because these elements are sorted, and we must be knowing that if array is already sorted, then we can apply the binary search. If we know this thing, if array is already sorted, we can apply the binary search over that. Okay, and binary search take log n time to work. Linear search take order of n time to work. Okay, so why we are not applying the binary search? Because we know that every time we are searching the position in the left side array, even after 25, if 10 is coming, again we will search in the all left side array, which will be sorted because 25 will be its exact position. Okay, तो हमारे पास ये sorted array है, जब हमारे पास sorted array है तो उसमें हम linear search क्यों अप्लाई कर रहे हैं? Can we apply the binary search or not to find out the position of 25? Yes or no? Please write in the chat box. Yes or no? Can we apply the binary search or not? Please write in the chat box. Can we apply the binary search to find out the position of 25 in this sorted array? आप बता सकते हो, बाइनरी सर्च अप्लाई कर सकते हो इस पे? Yes or no? Please write in the chat. Yes or no? Anyone, please write in the chat. Can we apply binary search in other algorithm if array is sorted? So you are asking another question, gate aspirant. Can we apply binary search in other algorithms? We can apply binary search if the array is sorted. Okay, binary search means we are searching that particular element. Okay, so we can apply binary search to, this is the precondition for binary search, that array must be sorted. Array must be sorted. Okay, this is the prior condition. Okay, so if you don't know about binary search, it's okay. In binary search, we simply go to the middle element. Because array is already sorted, we go to the middle element. Like here I compare with maybe like with 40. Then if I found that okay, this is smaller, 40 is still greater than 25, then I do not need to compare 25 with these two elements, because I'm sure 25 will be here at this place. Again, I will compare with the middle element, middle. So out of these three elements, 20 is the middle one. I see that 20 is less than 25. So I'm sure that 20 will not be at the left hand side. I will compare 20 with 30 only. So I will say that okay, 30 is greater than 25 and 30 is less than 25 and greater than 20. So 30 must come here. Okay. So we can apply. Yes, we can apply. Yes, the answer is yes. We can apply the binary search over here to find the position of this. And if we can apply the binary search, then for searching the position of 25 will take log n time rather than n time. तो नंबर ऑफ कंपैरिजंस कितने हो गए आपके पास? नंबर ऑफ कंपैरिजंस पहले कितने हो रहे थे? एन कंपैरिजंस करने पड़ रहे थे आपको, सभी से कंपेयर करना पड़ रहा था. अभी कितना करना पड़ रहा है? log n. क्योंकि आप बाइनरी सर्च अप्लाई कर सकते हो. हाँ, कर सकते हैं, क्योंकि वो सॉर्टेड एरे है, कर सकते हैं. और कर सकते हैं तो log n टाइम लगेगा. ठीक है, log n टाइम लग रहा है अपने को. और n एलिमेंट्स के लिए कितना टाइम लगेगा? n log n. n एलिमेंट के लिए कितना टाइम लगेगा? n log n. Then why we are not applying the, if this is possible to apply the binary search on the insertion sort, then why we are applying the linear search? Here we are applying the linear search. Okay, we are linearly comparing the element until I is greater than 0. 0th is the index. We are moving up to that. So one by one we are comparing, we are decreasing the I value. And let's suppose from 5, 4, 3, 2, 1 indexing. We're comparing with all the elements linearly. Why we are doing this? Why we are not applying binary search here? If we can apply binary search, then number of comparisons, one thing is sure, will reduce. For one pass I'm talking about, that will reduce to log n, or for n pass that will be n log n. Okay, so that will improve the number of comparison. But number of swap, how many will be number of swap? Or I can number of shift, how many number of shift will be there? Now I find out the position of 25. Okay, I know 25 will come at the place of 30. Now I know this thing. Okay, this element will come at the place of this thing. In how much time? In log n time. In how much time? For one pass, in log n time. Okay, but the problem is that even you find out this position in log n time, but again you need to shift linearly. You need to shift all the elements. all the elements. So shifting still will take, for complete algorithm, that will still take n square time, 1 plus 2 plus 3 plus up to n. So that will take again n square time. And if you will add both of them, then again that will asymptotically n square. N square plus n log n is n square. Okay, still asymptotically the complexity will be n square. So what I want to tell you is that these are the important points. You can note down what are the important points. First point is that we can apply the binary search to find out the position of an element in the left sub array, which is already sorted in insertion sort. Yes, we can apply. Yes, we can reduce the number of comparisons. Yes, we can reduce the number of comparisons, but the total complexity of the insertion sort still will remain the n square. Why? Because number of swaps still, number of shift, I have to say, number of shift operations still will be n square, because I need to shift only one by one. Linearly, I need to shift the element. It's not like that I'm shifting all the elements together. One by one, we need to shift all the elements. So in that, due to that, the complexity for shift operation will be n square. Comparison will be reduced. That will be n log n for all the elements. Okay. So still that will be n square. Still that will be n square. Okay. Okay. So any question in this you can ask. If any question in this you can ask. You will not find out, one thing I can ensure you, that you will not find out all these questions at one place. At least at one place you will not find out all these questions related to this sorting algorithm. Okay, so let's jump to the next algorithm, that is the merge sort. How merge sort work? Simply, let's suppose we have this array. In merge sort we use the divide and conquer approach. In divide and conquer, we divide our big array in two half, like half element will go this side, half element will go this side, again half, again half, again half, until unless we will be left with one element. Okay, after getting this one element, when we left with one element, then we will compare this element with this element, and we will say that, okay, which one is smaller? I will sort according to that. So 2 will come here, 5 will come here. Similarly here, 4 will come here, 6 will come here. Then I will compare these two and these two together, and I will sort them and I will put in here. So likewise, we are comparing these two and sorting them and finding it here, comparing these two, sorting them, finding it here, and then comparing these and these elements and sorting it here, then comparing this and these elements and finding out this complete sorted array. Okay, so this is how merge sort is working. Okay, this is how merge sort is working. Simple. Dividing the big problem, half element left side, half element right side, again half, again half, again half, again half, until unless we will left with one element. Okay, there may be zero element also at one side. So you will compare the last elements and you will sort them. You will start from the bottom sorting, and you will keep merging them. You will keep merging them. You will merge here these two and you will get this. Then you will merge these and these two, you will get this, and again like that. That's why this is known as the merge sort. This is how merge sort is working. This is how merge sort is working. Okay, so let me ask you one question now. One question from quick sort, merge sort. In which sequence, actually these are the functions you are calling. Okay, so these are the functions. Let's suppose this is function 1. In this function you pass this as an input. This is your input, you pass this. Okay, so then you will call another function, let's suppose function 2 and function 3. This function is having this as an input to sort. Okay, and so on like that. So this is function, let's suppose 4, function 5, function 6, function 7. These are sub functions we will call actually. Okay, function 8, function 9, function 10, function 11, 12, 13, 14 and 15. Okay, these are the various functions we are calling. So the question is, in which sequence merge sort functions will be called? Which function will be called first, and then which function will be called out of this, and then which one, then which one, then which one? Can you give me the sequence? Can you give me the sequence in which these functions will be called? And I can show you the code also. So actually in merge sort, you will keep in merge sort, actually what you are doing is you are calling merge sort actually two times. One is for the left function, one is for the right function. For left, n by 2 elements, and again n by 2 elements for the right, this. Okay, you will keep calling this. So this is the left function actually I'm talking about. This is the right function. So first we call the left function, and then we call the right function. This will keep dividing, and recursively we keep calling. Okay, recursively this keep calling. Can you write it? If you don't know, it's okay, you can write no, and I will tell you and we can proceed. And if you know, you can write. So in which sequence this function will be called? I have given the name to them: f1, f2, f3, f4, f5. You can simply write 1 2 3 4 5, like you do not need to write the f with that. You can simply write 1 2 like that. Okay, we get the answer. That's great. From Gate Aspirant 2023, he is saying that f1 will execute first. Definitely, this is our main function. Now we call two sub function, this function and this function, but the left function will be called first. F2 will be called first. This will be left function. So first we called F1, then F2. After that, again the sub 2 function will be called. One is left function, one is right. Before left will not complete, we cannot execute the right one. Okay, so F4 will execute, then F8 will execute. After F8, then which function we are calling? We are saying which function we are calling. This function we will call F9, and I think you given the right answer. So F9, and after this, which function we will call? We will call F5. Once the left part will be called, then we will call the right part of this. Once the left function is completed, then only we can execute the right function. Okay, but this, once the F8 is completed, then we executed once the F is done, we call the F9. And when this left part is executed, we will call the right part. In right part, we call this function first, F5. After that, again, we have two functions, left function and right function. So we will call the left function first, which is F10, then F11. Okay, and after completing this complete part, actually, its complete left part, actually, we call this, actually, we will call this right part now. In right part, we will call F3, and then I'm directly writing now F6, and then F12, and then F13, and after F13, let me write over here. Here we have space, F13. After that, we will call F7, and then F14, and then F15. Okay, and after this, that's it. That's it. We call all the functions. This is how we are calling the function. And another question they can ask you is that which function out of these function, which function will finish its execution first? Okay, you tell me only one function. Okay, you tell me only one function. No need to write about all of them. No need to write all the complete sequence. You just tell me out of these functions 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, out of these functions, which function will completely execute first, will finish its execution out of these numbering? Can you write the number? So we get the answer from Gate Aspirant, that is 8. This will finish first. Can you tell me the second one, gate aspirant? Can you tell me the second one? After finishing it, which function will execute? Which function will finish execution? Can you tell me that also? 9, that's great. And after that, one more, okay. Last I'm asking to you, which function will execute next? Finish first, next. Finish its execution completely. And that is 4. So you know you are executing. These are finishing. How these are finishing? These algorithms are finishing execution. So this can be the another question that can be asked. So you can answer this question only when you know about the merge sort. So in merge sort, we are simply dividing the elements in half, and half element will go to the left, half element go to the right. So from P to Q, like 0 to, let's suppose we have, let's suppose 0 to 9 elements. So 0 to, let's suppose we are finding half. So 0 plus 9 divided by 2, so that is 9 by divided by 2, that is 4. So from 0 to 4, elements will be passed in the left sub array, and in the right function we are passing from 5 to 9, means Q plus 1 means 4 plus 1, 5 to R, last 5 to 9. Okay, and after that we are merging them. Okay. Okay, so this is how merge sort is working. So let me take these last two questions from my side. What if odd number of here odd number of elements will be there, 0 to 8? Simple, same I will do. I am not doing something different here. Divide by 2, so that is 0 plus 8 divided by 4. So 0 to 4 elements will be in the left sub function, and from 5 to 8 will be in the right sub function. Okay, so you can modify it also. You can otherwise you can modify this also. You can write 0 to 3 here, or 4 to 8 here, but according to this now this is working like this. So definitely one element will be more either to the left side or right side. Here that is going to be more in the left side. Okay, here we have 9 elements, 0 to 8. So extra element will go here, in this case that is going to the left hand side. 5 elements are here, 0 to 4. 0 the index, starting from 0 index going up to 4th index, and here starting from 5th index and going up to 8th index. So 4 elements is at the right hand side, and 5 elements is at the left hand side. Okay. Okay. So any doubt you can ask. Otherwise, let me ask you one more question now. Merge sort is in place algorithm or not? Can you tell me what is in place algorithm? Okay, let me tell you what is in place algorithm. The algorithm which do not take extra space. The algorithm which do not take the extra space, they are known as the in place algorithm. Okay, the algorithm which do not take the extra space to sort the elements, they are in place algorithm. Selection sort is in place, bubble sort is in place, insertion sort is in place, but merge sort is not in place. Merge sort take extra space. Okay, so if you will go through how merge sort is working, how we are merging the sorted, how this function is working, then you will know that okay, we are using extra array. We are using extra array to merge these sorted sub arrays. So we know that half elements going to the left, half element going to the right. This will be sorted, these will be sorted. Then we need to merge them again. To merge these two, we are merging them here in this function. We need extra space. We need another array to merge the elements from this sub array and this sub array. So that we want to merge them, we need extra space for that. That's why this is not a in place. And another question is, merge sort is stable or not? Merge sort is stable or not? Let me tell you what is stable. What are stable algorithm? So in stable algorithm, the sequence in which you are giving the input, if you are getting the same sequence in the output, that algorithm is stable. Okay, let me take another line. in reverse order I am talking now. If the sequence in which we are giving the input is different what you are getting in the output, then that is not stable. Let's take an example now. So let's suppose I have element, I give you these elements 10, 20, okay, let's suppose 30, one more 10 I give you, then 40. I ask you to sort these elements. Okay, so you are giving me two algorithms, two algorithm 1 and algorithm 2. See how they are behaving, these two algorithm. Algorithm 1 is behaving like this. So let's suppose these two have the same value, 10 and 10. These two numbers have the same value. So let me give the abbreviation so that I can differentiate these numbers. Although these numbers are two different numbers, okay, they have same value, but they are two different numbers. Okay, although they have the same value. Okay, so I am just giving subscript here A and B so that I can know that okay, they are, this number come first, this number come later, this number come later, although they have the same value. Okay, so algorithm 1 give this as an output. Just a minute. So we are sorting the element. These are two sorting algorithms, algorithm 1 and algorithm 2. 10a, 10b, 20, 30, 40. So this is the output given by algorithm 1 and this is the output given by algorithm 2. 10b, 10a, 20, 30 and 40. So they see both the elements are sorting the numbers. Both the elements are sorting the numbers. This is also working fine. This is also working fine. 10, 10, 20, 30, 40. 10, 10, 20, 30, 40. Okay. But what's the difference? Algorithm 1 is giving the same sequence what was given in the input. The output, in the output you are getting the numbers in the same sequence in which you were getting in the input. In input you are giving this number later than this number. Okay, so in the output also you are getting this number later than this number. Okay, so this is actually stable sort. This algorithm is a stable sorting algorithm, but this is not a stable sorting algorithm because in the input b1 was 10, this number was given as an input later on, but this number was given earlier, although in the output they are in reverse order. 10b is coming first and 10a is coming later. So this is not stable. Algorithm 2 is not stable. Okay, algorithm 2 is not stable. Okay, so merge sort is actually stable algorithm. Merge sort is a stable algorithm. Okay, quick sort is not stable. Quick sort is not stable. Quick sort is not stable. Okay, yes, merge sort. Yes, merge sort is not a in place algorithm. That is not a in place, and that is stable algorithm. That is stable algorithm. Okay. So one question you maybe ask, what's the difference between 10 and 10? Why we are so much worry about their sequence in which the input sequence and output sequence is? It may be like that. Okay, you have the application of sending the signal. Okay, you are sending the signal from maybe from one location to another location through a satellite. There is a satellite, you're sending the signal. So you just want that even though you are sending the same signal, but you want that the signal should go in the same sequence. Signal should go in the same sequence, or the packets you are sending over the network, they must be in the same sequence in which you are sending, although some packets may have the same information. Okay, but you don't want to change the sequence. So in that case you will sort the packets using this stable sort if you don't want to change the sequence. But if you are not bothered about the sequence, you know that there is no impact, then you can use the algorithm 2 also, which is not stable. Okay, so actually that's it about the sorting algorithm. We talked about till merge sort. There is some these you can work on this thing. This question, actually this is gate question itself. Actually I just converted it in the form of this matrix, and this is very 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 important actually. So number of comparisons and number of elements shifted when we are merging two sorted array. So that they're asking what will be the best case of that, worst case of that. So you can think over this question first. How you can merge the two sorted array, like I'm saying that 1 2 3, this is one sorted array, another array is like this 4 5 6. How you will merge them? Or maybe 1 3 5, this is one sorted array, another one is 2 4 9. So how you will merge these two array so that you will get the complete sorted array? Okay, so what should be the technique? So that technique is used in the merge function of the merge function of the merge sort. Okay, and in that, they while applying this merge function, they are asking how many comparisons you perform, how many shift operation you perform in best case and worst case. So you can try this and you can write the answer in the comment box. Okay, okay, and that's it for today actually. Today we don't have more time actually to continue. So we already can get the answer from Prakhar. Prakhar already give the answer here. This will be minimum of a comma b. And what is a? A is the size of this array, b is the size of this array. Prakhar, please help us. Here, worst case. Worst case. In worst case number of comparison, you must be knowing about the how you are merging these two. Actually, what you need to do, simple. You will compare this element with this element. Whichever will be the smaller, you will store in the big array, in the sorted big array. Then you will compare this element again with 4. 2 is smaller, you will store. You will compare this element with this. 3 will store. Then 4, 5, 6. And in this case, again the same procedure will be same. Like comparing 1 with first element, which one will be smaller will come here. Now this is placed already. Now you will compare 3 with 2. 2 is smaller now, so that will come now. Now you will compare 3 with 4. 3 is smaller, so we will place 3. Now we will compare 4 with 5. 4 is smaller. Now 5 will be smaller than 9. Okay, so this is the procedure you are following. While following this procedure, the question is what now, how many comparisons you perform, how many shift operation you perform. Shifting means you are shifting the element from here to here, here to here. And comparisons mean you are comparing this element with this element, like you're comparing the elements in one subarray to the another subarray. The size of one array is A, the size of another array is B. So Prakhar, please help us to answer this or these three also, please. So this one, number of comparison in worst case, please tell us number of comparison in worst case, or anybody know, please try this thing. No, I'm just asking what is the worst number of comparison in worst case. Let's suppose size of left array is A, size of right array is B. In worst case, how many comparisons you need to make? See, this is the best case I have taken. This is the best case I have taken. When you see in the best case, you will compare only 3 times. How many comparisons you will perform? 3 times. Okay, one for this, one for this, one for this. That's it. Okay, so you will take minimum of A and B actually. So maybe here 2 elements are there only. So you compare 1 and 2. This is the one best case. Best case is this. This is one sub array. This is another sub array, let's suppose. So this is the best case. So number of comparison will be this much. How many? 2. 1, 2. That's it. And what will be the worst case? Worst case will be maybe alternatively you are comparing. Okay, alternatively. So how many comparison will be there? Let me write A plus B minus 1. For n elements, n minus 1. Last element you do not need to compare with anyone. And how many shift? See, shifting you are doing for all the elements. Even in best case, in worst case, you are shifting all the elements. So A plus B, A plus B. Okay, that's it for this. And that's it for today's session. Thank you everyone for being with me. Gate aspirant, you remain till the end. Thank you, Prakhar. You also answer this question. And thank you other people also who are right now with us and who remain in the session. So I hope this session will remain useful for you people. And believe me, these were the most important questions asked till now, till the much short we remain able to cover. But these still are very important questions from these sorting algorithms. So keep preparing. Best of luck. Thank you everyone for joining. So I'm now ending the session.